We are supposed to prove by mathematical induction the summation of r cubed from r equal to 1 to n will give us this expression here. Okay, we let Pn be the given expression first. Okay, then for step 1, which is the base step, we prove that P1 is true. So this is step 1. P1 is true, that means n will take the value of 1. The left hand side of the expression, this is the left hand side of the expression, the n take the value of 1. So the summation will be r start from 1 and n at 1, r cubed. And this will give us 1 cubed. Okay, r start from 1. Okay, you substitute 1 into here, and it's supposed to stop at 1 as well. So the summation of this expression will be just 1 cubed, which will give us the value of 1. For the right hand side, we're supposed to prove this expression with n substitute by 1. Will give us 1, and this is equal to the left hand side. Therefore, P1 is true. In step 2, we assume Pn is true. So what is the Pn expression? The Pn expression will be just this expression. So I'm going to write the Pn expression here, and we are assuming that this is true. Step 3 is the induction step. For step 3, we are supposed to prove Pn plus 1 is true. So what is the expression for Pn plus 1? For Pn plus 1, in this side of the expression, we are supposed to replace the n here by n plus 1. And we will get this expression, r start from 1 all the way to n plus 1. And here, we are supposed to replace the n here by n plus 1 to get the Pn plus 1 expression. Okay. Replace the n by n plus 1. n plus 1 plus 1 will give you n plus 2. Okay, and we are supposed to prove this expression. This is the Pn plus 1 expression. Okay. I would like to prove from the left hand side of the expression. Okay, because it's a expression that we can simplify further. So I start to prove from the left hand side. Now this expression here can be expressed as summation of r equal to 1 to n. Instead of n plus 1, I stop at n, plus the summation of r equal to n plus 1 to n plus 1. Now these two expressions add up can give you this summation is because for this summation here, r start from 1 to n plus 1 means r equal to 1 to r equal to 3 until n and n plus 1. Okay, r until start from 1 until n plus 1, and this is same as the summation of r cubed from r equal to 1 to n. That means we're going to add up r equal to 1, 2, 3 until n, r equal to 1 to until n, plus because we're supposed to stop at n plus 1, so we plus another here stop at n, so I continue to add the last term, and the last term is n plus 1. We start from n plus 1 and n plus 1, which is this last term here. Now this expression here we can usually simplify from step 2. From step 2, we know that the summation of 1 to n r cubed can be simplified into this expression here. So we are going to substitute, we are going to replace this expression by 1/4 n square multiplied by n plus 1 square. So this will give us 1/4 n square multiplied by n plus 1 square. Now for this expression, the r start from n plus 1 and n at n plus 1. Okay, so I first substitute the r by n plus 1 into this expression here, r cubed. It will give me n plus 1 cubed. Okay, and my r is supposed to stop at n plus 1. Okay, so I substitute r by n plus 1 here, and I stop at that expression there. Now this is the expression that I'm supposed to prove. I'm comparing my expression obtained here with this expression. They have a 1/4 n plus 1 square, which I can easily take out from here. Okay, so if I take out the 1/4 n plus 1 square, I will have a n square here and a 4 here because I took out a 1/4. Okay, so I'll have a 4 here. 4 times 1/4 will give me a 1 here. Okay, and n plus 1 square is taken out, so I left with a n plus 1. Okay, so if I were to simplify this expression, this whole expression, hopefully I can get this expression. Okay, so from here, n square plus 4n plus 4. If I were to factorize this, this will give me n plus 2 square, which is equal to the right hand side of the expression. Okay, so shown. Therefore, Pn, if Pn is true, we have proven that Pn plus 1, okay, is true as well. Therefore, in conclusions, since we know that P1 is true in step 1, by Mi, Pn is true for all positive integers of n. Therefore, we have proven that Pn, which is the given expression here, is correct. Before I end this question, I would like to talk about another notation for step 2 and step 3. It's quite common that instead of assuming Pn is true, okay, we sometimes assume Pk is true. Okay, it's just a change in the symbol. Instead of using n, we use the k. And because we use k, this whole expression here has to be rewritten as summation of r equal to 1. Instead of n, it will be k. And equal to 1/4 n squared. Instead of a n, it will be a k, and k plus 1 square. Okay, so this is the pk. This is the pk. And similarly, if we change, if we replace the pm, if we rewrite the pm by pk, here we have to rewrite as pk plus 1. Okay, so pk plus 1 will be summation of r equal to 1 to k plus 1 r cubed equal to 1/4 k plus 1 square k plus 2 square. In short, it's okay to write as Pn, and it's equally okay to write as Pk. Okay, there's no difference. Okay, this is only a use of different symbols.